This video is about the effect of the gain bandwidth product of op-amps on negative feedback amplifiers built from those op-amps. It corresponds to section 19.5 of the Applied Analog Electronics textbook. Now, we're going to start with a little bit of notation. I'm going to use A to be the open loop gain. This is the gain that you have from the op-amp itself. That is not when it's in the feedback loop, but just when it's not having any feedback at all. And in the past, we've treated it as if A was infinite. And that's, in fact, generally how we design initially when using op-amps. We've got B, which is the feedback gain. Now the feedback is just our voltage divider, so it is going to be of the form Zi over Zi plus Zf. Alright, what we need to do now is figure out what the closed loop gain is. And I've got a derivation in the book based on various formulas that we've derived previously, but it's kind of tedious and messy to go through the details of that. It's in the book if you want to look at it, and I'm just going to give you the results here. And there's two different closed loop gains we're going to get. One for when we've got an inverting amplifier, and when we've got non-inverting. So for the non-inverting one, we're just going to have A divided by 1 plus AB. And for the inverting one, we'll have A times B minus 1 over 1 plus AB. Okay, we should check whether these closed loop gains, so these are closed loop, that is with the feedback. We should check to see whether as A goes to infinity, these do the right thing. So what happens if A goes to infinity here? For this one, well, 1 plus AB, when A is going to infinity, that means that AB is getting big enough that the 1 doesn't matter anymore. The A's will cancel, and this will go to 1 over B. Well, what is 1 over B? Well, that would be flipping this thing upside down. 1 plus Zf over Zi, which is exactly the gain that we have claimed in the past for a non-inverting amplifier. What about for this one? Well, as A goes to infinity, we again have the same phenomenon that AB is going to get so large that 1 doesn't matter. The A's will cancel. We'll get B minus 1 over B. And we can simplify that by saying, well, what's B minus 1? That's going to be minus Zf over Zi plus Zf divided by B, which is Zi over Zi plus Zf. And that just simplifies to minus Zf over Zi, which is indeed the formula that we've used in the past for inverting amplifiers. So this formula, all I've shown you here really, is that this formula, as you take A to infinity, goes to the value that we expected it to. All right. What do we want to do, though, now to treat gain bandwidth product? Well, what is it that we're really dealing with here? What we're dealing with is the fact that our op-amps do not have an infinite gain, and in fact they don't even have a constant gain. They have a gain that decreases with higher frequency. In fact, they're usually carefully designed so that the gain is minus J times a constant over frequency. So on a Bode plot, on a log-log plot, it's a straight line going down 1 decade per decade. And this constant here is the thing that's called the gain bandwidth product. All right. What I want to do now is to take a look at this closed loop gain, not as A goes to infinity, but as A has this value. Now, you notice that if F is very small, if we're looking at very low frequencies, then this thing does go to infinity. So the approximation that we were using here previously is good for very low frequencies. We worry about gain bandwidth product, about this non-infinite gain, mainly when we're looking at higher frequencies. All right, so let's do the plugging in. I'm going to write stuff down again. So what I want to look at is A over 1 plus AB. That was the closed loop gain for the non-inverting amplifier. And I want to do it when A is equal to minus J times this constant FGB over F. All right, so if we plug that in, we get minus J FGB over F over 1 plus, or I'll take it 1 minus J FGB over F times B. Now that looks kind of messy. What I'm going to do is I'm going to multiply top and bottom by this thing that's on top here, so I'm going to get 1 over something. So I will have 1 over, and then I will have F over FGB, instead of having the minus J on the top there, I'll put the J up here. It's the same thing, and then since I was dividing by that, this is going to cancel here, and I'm going to get plus B. And that looks fairly reasonable, but I actually want to do one more thing here, and that is I want to take it to be equal to 1 over B times 1 over 1 plus JF over FGBB. Why do I want to do it like that? Well, this is exactly the formula we have for a low-pass filter. This is a low-pass filter which has got a passband gain of 1 over B, and then rolling off at 1 decade per decade with a corner frequency of FGB times B. So our non-inverting amplifier behaves like a low-pass filter, and if we take the gain, which is 1 over B, and multiply it by the corner frequency here, the bandwidth of this filter, we get the gain times the bandwidth is just FGB. And that's why we call this the gain bandwidth product, because it's the product of the gain and the bandwidth of the op-amp. So what does that mean? Well, it means that as you adjust the gain of your amplifier, if you ask for a very high gain, you're going to have a low corner frequency, because this line here is always basically staying in the same place. And if you want a high bandwidth, you have to limit yourself to a low gain. Let's take a look at that as a result of measurement. This is really true in the real world. So I did a bunch of measurements. And the measurements I did were of the MCP 6004 op-amp, the one that we tend to use in class. And I used the network analyzer on the Analog Discovery 2 to look at how much gain I would get. And I set this thing to have different gains by changing the resistors. So I did a unity gain amplifier. I did one where the gain was 2, so the two resistors were the same. And then I just kept increasing the feedback resistor to get more and more gain. And you can see that there's a fairly simple relationship here. The gains are, if you look at the different colored lines there, the gains are the ones that you would expect at low frequency. It behaves just like we would have predicted with the A being infinity. And they all kind of fall along the same line there. I drew the line there that corresponds to the specified gain bandwidth product of the MCP 6004. So this actually is looking like it's doing pretty much what I said it would do. We can go a step farther and say, well, what happens if we plug the model that we had in? That is to say, we say this formula, this is how the amplifier is supposed to behave. How well does that predict it? you can actually take the data that you made measurements from and fit it. You've got two parameters here. What's the gain bandwidth product and what's the B. And we can look to see how well it fits. For that matter, we know what B should be from the pair of resistors we use. If we plug that in and we can just fit the gain bandwidth product, we can use this to measure the gain bandwidth product of an amplifier. So let's take a look at doing that. I did that for three of those curves that I showed you on the previous slide. One with a unity gain at the bottom, one with a medium sort of gain. It was 100 over 5.1, so a little less than 20. And one with a large gain, 2 megohms divided by the 5.1K. Actually, these were all non-inverting, so 1 plus 500 over 5.1 and 1 plus 2 million over 5,100. Okay, the curves there in the thin lines are the data. The fat yellow curves that are highlighting them are what the model says they should be based on fitting to get a gain bandwidth product, not of a megahertz, which is what the spec sheet said it ought to be, but of 838 kilohertz. And they fit pretty well, particularly for the higher gain ones. So this is looking like the model actually does a pretty good job of capturing what's going on up to about a megahertz. Or, yeah, megahertz probably is okay. Once you get beyond that, though, you can see that the behavior differs enormously. The yellow line is no longer highlighting the other things. And that's because there's a deliberate design in the op-amps that once you get above the gain bandwidth product, once you get above that frequency, they do some extra stuff in there to suppress higher frequencies, so you don't get oscillation and stuff. So the model in the region where we want to use this thing is actually quite good. And that's why people use the gain bandwidth product models, because the op-amps are designed to have that gain of minus J times FGB over F. Now, you notice I put the minus J in here in all my computations there, but you don't see it here in this picture because it's just looking at the magnitude of the gain. And we were just looking, sort of not paying attention to what's happening to the phase. That's actually fairly important to look at what happens with the phase, because when AB is getting close to 1, that is to say, when we're getting close to the corner of our low-pass filters here, the phase starts mattering. And on that downward slope there, the phase is quite different. So in the pass band, this thing actually does behave pretty much like it's got a real gain. But once we get into the downward sloping part, there is a phase change, and that sometimes will matter quite a bit. For the most part, though, when we do these gain bandwidth computations, what we're doing is looking for what is the gain in the pass band, how wide is the pass band, what bandwidth can I go up to before I start running into the limitations of the op-amp. And the computation there is very simple. Take the gain bandwidth product, divide by the gain you want, and that's your bandwidth. That's where the corner is going to occur on these plots. The other thing you might notice here is that the MCP 6004 is spec'd to have a 1 megahertz gain bandwidth product, but when I measured it, I only got 838 kilohertz. That's actually not all that unusual. The gain bandwidth product is usually 80% to 120%, something like that, of the specified one. It's not a tightly controlled parameter. And so you don't want to count on, hey, I can get a gain of 100 here, and I'll have all the bandwidth I need. Leave yourself some extra slop there, because the gain bandwidth product isn't all that tightly specified. Okay, so from a design standpoint, all you really need to worry about is that your gain bandwidth product tells you the limitation on your gain for a particular frequency, or the limitation on your bandwidth for a particular gain. And this is one of the reasons why people generally don't design negative feedback amplifiers with very high gain, because if you do that, you get a very small bandwidth. If you want to get a larger gain, you do multiple stages, each with a small gain. And you can get a high bandwidth with that small gain, and as you run through multiple amplifiers, you can get your large gain without losing the bandwidth. Okay, I gave you the results here for the non-inverting amplifier. The inverting amplifier has got the same corner frequency. You can go through and do the algebra and get exactly the same filter specs. The only difference is what your passband gain is going to be. Your passband gain is going to be B minus 1 over B. Remember, that was the gain that we had when we were not paying attention to the gain bandwidth product limitations. So that's just the minus ZF over ZI. That's the gain you're going to get in your passband. But the corner frequency is still the gain bandwidth product times B. Okay, that's probably all you really need to know about gain bandwidth product for this course.